we've discussed velocity and acceleration theoretically, and then we've diagrammed it and talked about an example. But let's do some practical, concrete examples of computing velocity and acceleration at specific points. Now, we're given two separate position functions, and we're asked to find the velocity and acceleration at time 4 here, and velocity and acceleration at time 0 here. So let's go ahead and get to computing these things. Now, recall that the velocity is simply the derivative of the position vector. So we would say that v of t is 2ti plus 1j plus 3t to the 1/2 k. So that's like the square root. And a of t is the time derivative of the velocity vector. So that's 2i plus 0j plus 3/2 t to the negative 1/2 k. Now, I'm going to rewrite that in a way that's probably a little more convenient to compute. So the first was 3t to the 1/2, so I'm going to write 3 square root of t, and I'm going to write 3 divided by 2 square root of t here. And maybe that'll make our lives a little easier. So then to compute, I say v of 4 is 8i plus j, and the square root of 4 is 2, so we get 6k. All right. Now, similarly, we don't have a t here, so that's just 2i. Whoops. And there's no j here. And again, square root of 4 is 2, so we have 3/4 k. All right, well that handles it for this one. Now, what I notice on this particular position function is that I have an e to the t in each component. So what I'm going to actually do is I'm going to rewrite r of t as e to the t times cosine t, sine of t, and 1. And this may not make our lives easier, but it's a good reinforcement of a skill that we learned. So if we come over here, what we notice is that if I have some sort of scalar function multiplied by a vector valued function, then its derivative looks like a product rule. So we'll need the derivative of the scalar valued function, and then we'll need the non-derived form of the position function and the derived form of the position function. So if wt is equal to e to the t, well, w prime of t is also e to the t, so that kind of makes our lives easier. So since those are the same, in this particular case, that these being the same function, we get to kind of cheat and simplify to this. But in general, you can't do that. But the whole point of these properties is that when it's convenient to do it, we get to do it. So it's all about being clever. Anyway, so if this is like a u of t, right? So over here, we're no longer using this r anymore. We're more so using like a u of t here. Then u prime is negative sine of t, cosine of t, and 0. So that tells me that my velocity is instead, it's going to be this multiplied by the sum of this and that. So it's e to the t cosine t minus sine of t cosine of t plus sine of t and 1. So that's the idea here. Now if we want to do the same thing, we can call this u of t. So u prime of t is this thing's derivative, getting us negative sine of t minus cosine of t, negative sine of t plus cosine of t, and 0. So then, our acceleration function is, or our acceleration vector value function is e to the t, this plus that. So those cosines cancel, so you have negative 2 sine of t, this plus that, the sines cancel to cosine of t and 1. So now that we have v of t and a of t, we can get v of 0 and a of 0. Now remember that e to the 0 is just 1. So for practical purposes, we don't actually have to consider this scalar function at the edge. So I'm trying to figure out the best place to write this. So then v of 0 is cosine of 0 is 1, sine of 0 is 0, cosine of 0 is 1, and of course 1 is 1. And then your acceleration at 0, well that's 0, that's 2, because that cosine of 0 is 1. So all that work simplifies pretty cleanly here. So that's how you compute derivatives for that's how you compute acceleration and velocity for vector valued functions at a point.